Good day and warmly welcome, also on behalf of Carsten Urban and Konstantin Greif, to everybody who is new to this lecture on high performance computing. If you're new to this course, you are at the right place. Due to the current situation, we offer you the lecture High Performance Computing 2 for the first time as online course. Online learning, possibly new to you, will be new to us too. Let's accept the challenge for the next 12 weeks. Guten Tag, meine Damen und Herren. Ich begrüße Sie recht herzlich, auch im Namen von Carsten Urban und Konstantin Greif, zu der Masterveranstaltung High Performance Computing 2 an der Universität Ulm. Wir haben uns dazu entschlossen, die Online-Version dieser Veranstaltung in Englisch aufzuzeichnen. Es sollte Sie aber nicht davon abhalten, Fragen im Forum über Moodle an Herrn Urban, Herrn Greif oder auch an mich in englischer oder deutscher Sprache zu formulieren. Also es geht jetzt auf Englisch weiter. Let's accept the challenge for the next 12 weeks. And now let's continue with our introduction. At the beginning, a few topics to be discussed. So, as already mentioned, the lecture will be offered as online course. All materials will be given in English. However, the communication with the lecturers is possible in English and German. Additional material can be downloaded from Moodle, and the lectures will be uploaded every Monday at 8 a.m. early in the morning. A few comments about the course grading. There will be weekly exercises which have to be solved individually and submitted to Moodle. There will be project at the end of the term where the solution and its documentation will be graded. And we support collaboration, so you may collaborate with anyone, but it's required to write the code independently and write names of all collaborators on submission. So probably we'll be running a code similarity program on all solutions. Here are a few photographs of Carsten Urban, Konstantin Greif and me. These are the people behind this online course. The learning objectives. So at the end of the term, you should be able to understand, apply and explain numerical methods for modern computers, parallel computers, GPUs, or probably also vector computers. You should be able to realize these schemes into efficient software. You should be able to successfully apply these methods for an application and also present the results of a project. During the lecture, there would be one main model problem. So at the beginning, we start with the modeling brushless DC directed current motor, starting from scratch using Maxwell's equations, and see that these equations, after simple modeling style, will end up with a 2D model, some nonlinear modification of the Laplace or Poisson problem. While we're doing all these high performance computing, a few comments about asymptotic complexity and efficient algorithms. So probably you know Moore's law, which says, or the implication of Moore's law is that the chip performance roughly doubles every 18 months. So why we should think about efficient algorithms and asymptotic complexity, just wait and you get a faster computer. Let's consider two simple examples. The recursive version versus an iterative computation of Fibonacci numbers, or the reordering rows and column before computing Gauss decomposition. Consider the Fibonacci sequence. So you start with f of 1 is 0, f of 2 is 1, and then we have for n greater than 1, the current relation fn plus 1 is equals fn plus fn minus 1. So why shouldn't we think about a recursive program to compute fn? Just these 4 lines, or let's say 3 lines, will give the result. So we start to compute f6, we have to compute f5 and f4. To compute f4, we have to compute f3 and f2. f2 is equals to 1, and to compute f3, we need the sum of f2 and f1. And also on the left side of this tree. How can we estimate the amount of work? Just simplify everything, and we only count the additions, not the traffic to the memory, nothing else. So there would be no addition to compute the work for f1. There's no work to compute f of 2, which is w2. And then if we add 2 numbers, okay, it's the work for, let's see here, the work to compute f5, the work to compute f4, plus 1 additional addition. So then we end up, okay, this recurrence relation is equal to the recurrence, or the function is the same as fn minus 1. Probably you know from analysis the asymptotic expansion for the Fibonacci numbers, which behave mainly 1 plus the square root of 5 over 2 to the power n, which is big O of 1.61 approximately to the power of n. Contrary, if we have the iterative algorithm for Fibonacci numbers, what we have to do, we just calculate, we're doing this for loop, and this there are less loops than n because we start at 3, and in the for loop we move this result to this memory, this to this memory, this variable, and just 1 addition. So the amount of work here is fixed. We are doing this loop at most n times, or we can estimate, we can give an up about as a big O of n. So what's the difference now between if we go back here, we have a big O 1.61 to the power n. Here we have O of n. What makes the difference? Okay, just a really rough limits of computation. So the fastest computer, if you have a look at top 500, if you have a look at the top500.org, where the fastest computers are listed with the data from the beginning of April. So the fastest computer has a peak performance of 148.6 petaflops. So petaflops, I had to Google what peta means. It's 10 to the power 15. So this can be written as 1.486 times 10 to the power 17 floating point operations per second. What a huge number. The number of seconds from the Big Bang, Urknall, is approximately 10 to the power 21. So if we take the whole time from the Big Bang till now, we had this very fast computer. We would be able to compute 10 to the power 38 flops just by this computer. Okay, we can probably took these computers 500 times, but it's just an upper limit will be 10 to the power 40. It's really academic, but it's an upper limit. What about the possible available memory? Okay, if you think about, okay, what we have to save, assume there would be some spin of the proton, if it's plus or minus, and we could use all protons which are available in the visible universe. So it's approximately 10 to the power 39, which is also a rough upper bound for the possible memory. Even if we have these very fast computer with 10 to the power 17 flops, or let's say 10 to the power 40 flops available from the Big Bang till now, with the recursive program for Fn, we could only compute Fibonacci numbers up to n around 184. Ooh. Of course, with the iterative method, we could compute Fibonacci numbers much higher, because here we have the linear behavior of this method. Okay, this is the method. Here we have the same method, but we have a slightly different data. So, probably as you know from first classes on computational mathematics, we would like to compute the LU decomposition of this matrix. Looks like an arrow, right upper arrow matrix. As you see here, okay, we have to eliminate the element 2, 1, or the first element below the diagonal, the next one, and so on. But if we eliminate these entry here by this we get some fill-in. So by eliminating, where's the mouse? By eliminating that's strange, okay. By eliminating the first element, we get fill-in, and the resulting LU, the lower triangular matrix and the upper triangular matrix, will be totally filled. So the whole triangular part and the whole upper triangular part will be filled. So even this matrix has only 3 times n minus 1 entries, the LU decomposition will have n squared entries. And so the inverse of L and the inverse of R will be not linear in n. What about if we reorder in such a way that the arrow is directed to the lower right? So just renaming. It's obvious that if we build the LU decomposition, we only have to eliminate entries in the lowest row. So the amount of work we have to do is just in capital O of n. That means for a matrix of dimension 1000, that will be much faster, so speed up by a factor of 1 million. And on the other hand, the storage of the LU decomposition will also need only storage of 3 times n instead of n squared. So here we have the same algorithm, but a look at the algorithm, we change a little bit and get a much more efficient version of our much more efficient way to do this. At the beginning I mentioned that we will try to solve efficiently on a parallel computer. We would like to apply some kind of numerical method, finite element method or finite difference method, which discretizes the operator or uses a simplified approximation to the solution by piecewise linear functions. But we start at some point with the Poisson equation. And we start with the Poisson equation with a very simple domain, let's say the unit square. And we have a right-hand side, which is equals to 1. And the solution is bounded on the the boundary. This is the boundary data. So we're using this equation because we know a lot about the solution of this equation. We know the exact solution, which is given, depicted here. And this nice situation that we know the exact solution, we can compare all numerical results we have. We also know the eigenvalues of our operators if we have a structured grid we are using on the units square, and we can exactly write what will be the exact convergence rate for the Jacobi method, for the Gauss-Seidel method, block versions of Jacobi and Gauss-Seidel method, and we have also, with a little bit of analysis, can compute the asymptotic expansions. So if we consider linear iterative solvers, we have this toy problem. We can see, okay, we will probably get these results, and what are the consequences for these results. We have a matrix, or the numerical methods we are considering, find elements, find differences, will lead to sparse matrices. It means we have a lot of zero entries in the matrix, and we have some kind of structure that we are able to use this information about all these zeros. So they are not randomly. First question is how to store these matrices if a lot of these entries are zero. And there is no straightforward way to do this. So at the beginning we'll have some comments about matrix data structures. Let's say some easy ones that you store the entry and the column and index vector as given here. So the 1, you have 4, 3, the I and the j index, and so on. Here, so the values -1, -1, or much more complicated sparse block compressed row storage, which is more favorite for vector computers. After we will have some analysis of these data formats for sparse matrix, we continue, and we will discuss the implementation of the finite element method. We're using the simplest piecewise linear functions, globally continuous, and all we have to do, we have to compute matrices where the matrix entries are given by this formula, or the right hand side vector bj is given by this formula. Looks quite complicated, but if you, after a few minutes where you look down what you have done, you will see that everything can be done, consider this part, just by these 6 lines. So it couldn't be that complicated. We understood, okay, it's necessary to have storage schemes to store our sparse matrices. We have the method behind the finite element method. But then we would like to implement this method on a parallel computer. So we start by a very simple problem. We start by a tridiagonal matrix. So tridiagonal matrix, you have this diagonal, you have a sub and a super diagonal. And these belong to 4 processors given here by these different colors. We cannot apply the standard Gauss elimination. There's a lot of communication. But we can take advantage in this way that we eliminate as far as possible on each subdomain. So we end up with this pattern. And now a closer look shows that we only now have to solve a problem, which is just also again a tridiagonal system, but it's now only of dimension 4 times 4. In general, if you have a tridiagonal matrix of arbitrary dimension and you have p processes, the whole communication is just a few data to one master processor and then solve a problem of dimension p, distribute the solution, and all the other stuff can be computed in parallel again. So what is all these techniques of parallelization behind? That should be, okay, there are a few jobs which can be done separately, but at some moment we have to do some communication. And we'll see how these communication is necessary. Are there methods, numerical methods using less, and also how can this communication be done? I started in the example before that I mentioned, okay, we have some tridiagonal system split onto up to p parts. For each processor you have one part, and it's easily done. So divide the numbers 1 up to n. So probably there's difference between the work for 2 processors is just 1, if it's not a multiple of 2 of p. How can this be done if you have some geometry, you have some problem behind, some domain? This domain is partitioned with triangles, and how we can split up that each processor, the same speed of all processors, will get the same amount of work. And this topic will be discussed in the lecture about partitioning. If you just have a square, okay, just cut it always. If the domain is more complicated, there are different methods to do this, and even how to grade what is a better method. We get some quantities. So now we're in a situation, we have our method, we have fast solvers, fast serial solvers. But how we can do this after we split everything, and how we can introduce methods where we have only a few, or where the amount of communication is very small. So that's the topic of domain decomposition. And that's, let's say, the schedule of the whole lecture of 12 lectures given by Carsten Urban and me. And that's already the end of the introduction. I hope you enjoyed the introduction, and then see you next week.